In this lecture, we're going to start looking at some proof techniques. Recall that we have the implication, which last time we defined as the statement P implies Q, or if P, then Q. Okay. For example, if it snows, then school is canceled. Okay, and it's an example of a proposition. Maybe true or maybe false, but it's one or the other. Okay, so we have the implication. What we can do now is form some related statements. For example, what if we look at Q implies P? That's a different statement. So that would be if school is canceled, then I guess the idiomatic way to say it would be then it must have snowed, right? Then it snowed, yeah. Okay. Sometimes you have to rephrase it slightly. We could also look at not P implies not Q. What would that look like? So if it's not true that it snowed, so if it doesn't snow, that is not P. If it doesn't snow, then school is not canceled. School is open. Or yeah, school is not canceled. And what's missing? I guess we can do one more. That would be not Q implies not P. So these are all implications that we can form from the original one. And this one would be if school is not canceled, then it didn't snow. Okay. All right, so we have 4 statements here. These all have names. So this one here is called the converse, if you just swap Q and P. This one is called the inverse, if you put knots on both of them. And this one, if you swap them and put knots, then you get the contrapositive. Okay. And so why are we looking at these? Well, it's because there's a very important and useful observation that we can make here. And so I want to ask you the following question. Suppose this statement is true, the original one. Suppose this is true. I'm not saying it snows is true, but this if statement is true. So meaning if it does snow, then school is canceled. What does that tell you about these 3, if anything? So is it true that if school is canceled, then it snowed? Well, no, not necessarily, right? School could be canceled for other reasons, right? So this being true does not imply that this is true. If it doesn't snow, then school is not canceled. Let's think about that. So if it doesn't snow, then school is not canceled. Well, it kind of has the same problem as a converse. So if it doesn't snow, we have no idea. Like school could have been canceled for some other reason, right? Let's look at the last one, which seems like it's the furthest away. But let's see what it says. So if school is not canceled, then it didn't snow. So if school is not canceled, that seems true, right? Because if school is not canceled, it didn't snow. Because if it had snowed, right, then school would have been canceled, right? So if it's not canceled, we can definitely conclude that it didn't snow, right? So it turns out that the contrapositive and the original statement are equivalent. You can even try to write out their truth table. Remember we did that last time for the implication here. But these, and they'll have the same truth table. So these are equivalent statements. And that's a very useful observation, as we'll see later on. Okay, in any case, let's get on with the actual proofs. So how do we actually prove something of this form? A lot of math statements have this form. Right, so how do we prove a statement or proposition of the form if P then Q? And really, there's not that much to it. I mean, the proof can be very complicated depending on the exact statement. But the first thing you should always try is the direct proof. There's not much to it logically, at least. But yeah, again, the proof can be very complicated. But here's the idea. The idea is you start by assuming that P is true. So assume P is true. Okay. If P is false, it doesn't matter. You might remember the truth table. If P is false, then the statement is sort of true by default because the condition doesn't even apply. So we have to assume that P is true, and we want to show that Q is true. That's all there is to it. Again, I'm kind of making it sound simple, but it's often not very simple at all. So yeah, we assume P is true, and we conclude, at the end of the day, we want to conclude that, so we want to show that Q is true somehow. Somehow, right? There are steps in here, right? So various math steps. Okay. And I don't want to deceive you. So sometimes, like when you see a math book, the proof almost looks like this. So you have P, they assume it's true, they do some steps, and they get to Q, just like that. That's almost never how it actually happens, and that's not how you should think about proofs. So this is an inaccurate picture. Maybe a more accurate picture of the process, at least, is you have P over here, you have Q over here. I'm trying to get from here to here. I'm trying to assume this is true, and then we can make some logical deductions. So maybe we can move a little bit closer to Q. And then we try something else, and that ends up over here. That didn't work. So then you come back and you say, okay, maybe I'll try this instead. And then I'm going to try something else, but I end up over here. I'm kind of stuck. So maybe I can work from the answer and say, okay, what if I prove this thing instead? I can show that that implies Q. So can we somehow prove that? Well, we could try to sort of retrace our steps here, and I mean, you get the idea, right? So this is a more accurate picture. This is a more accurate picture of the actual process. Okay, so I don't want to lead you to think that it's always a simple process. Logically, though, this is what you do. We should immediately look at some examples. So let's start with something we're all familiar with. The only way to learn this is to do a bunch of examples. So I'm going to do a few just right here in lecture. So if x and y are even numbers, it's by even number, I mean, they have to be integers if we're talking about even and odd. So I'll just make it clear. They're even integers. Then x plus y is even. That's a true statement. Let's prove it. Here's the idea. So you prove it. How do we prove it? Okay. Well, here is the first thing that a lot of people will try to do. So let's try to think about why this is true. So let's say we have the integer 6. That's an even integer. And we have an integer 4, right? That's an even integer. I'm assuming P is true. So we have 2 even integers. There are my 2 even integers. And I want to show that this is true. So we add them. And what do we get? We get 10. That's even, right? So this is an even number. So we're done. But no, this is actually not a correct proof. Not a correct proof. Do you see why that's not a correct proof? It's because we just did it for one example, right? So this is claiming that if x and y are even integers, just any two even integers, doesn't matter, that's always going to be even, right? So it's not enough to show it for one example. I mean, if you show it for a bunch of examples, that builds up the credibility of this statement, but it doesn't prove it. Like, we need an airtight mathematical argument that's always going to be even, no matter what even numbers we start with. Okay, so that's not enough. So we need to be more general. And so how do I write down two even integers? And this is where you often want to look at the definition. We have definitions for everything. So a definition of even, for example, let's recall what that is. X is even if, what does it mean to be even? Well, here's one definition. If x is 2 times an integer k for some integer k. Right? So to form 2k for some integer k. That's what it means to be an even number. Similarly, odd, what would that be? Will be one more, it'll be 1 off a multiple of 2, right? So odd would mean, so to form 2k plus 1 for some integer k. We only need even for now. So here's how I will proceed. I will assume this is true. I assume we have two even integers, any two even integers. So let x and y be even integers. And I'll say x is going to be 2k because it's even. So by definition, it's 2 times some integer k. And y is going to be 2 times, I don't want to put the same k because it's a different integer. So I'll put L. Some other integer. Let these be two even integers, right? Okay. Then x plus y. We want to show this. So let's start with, we have our two even integers. How do we show this? Well, we have to take a look at x plus y. We want to show it's even. We don't know that in advance. So let's just take a look at what we get. We get 2k plus 2l. All right. We want to conclude that's even. I can't just say it is, though. Like, is it actually even? Well, let's stare at this for a second. Is this 2 times some integer? Ah, yes, it is. I can factor out to 2. It's 2 times that integer. See what I did there? By factoring out to 2, this makes it very clear it's of this form, right? So this is even. We're done. That's it. That's the proof. Let's write a QED. Often you write QED at the end of the proof, which is Latin for, look at that, I proved it, basically. Sometimes you actually put this box too. Fill in a box. It's a QED symbol. Okay, great. Let's do another one. Let's do a biconditional this time. So, okay, how do we prove a biconditional? Biconditional. What's a biconditional again? That's P if and only if Q. Remember, the symbol's a double arrow. So yeah, again, that means P if and only if Q. So the if goes both ways. It's saying P, the statement and its converse are true. Recall what does this mean exactly? Recall P implies Q is equivalent to P implies, P if and only if Q is equivalent to P implies Q and our and symbol, and Q implies P. Okay. So how do we prove a biconditional? Well, this is basically telling us how. It's a two-step process. This is going to be true if that's true and that's true. So it's a two-step process. Whenever you're trying to prove two things are equivalent, or you have a if and only if, this is the process. You first prove P implies Q. I mean, it doesn't matter which order you do it in, but you can prove P implies Q, and then you prove Q implies P. And then we're done. We need both of those to be true. Okay? So if one of these is false, the biconditional is false. We need both of them, and we need both of them to be true. All right, let's try one of these. So let's try to prove. Let's try to prove. I emphasize the try, by the way. You can see why. So let's try to prove that x and y are even. So same setup as before. If and only if x plus y is even. Okay. Here's my P. Here's my Q, let's say. And how do we do it? How do we do the if and, oh, sorry, I forgot. If and only if. How do we prove an if and only if? We do that way and then that way. So we have this implication and that implication. So let's prove P implies Q first. If x and y are even, then x plus y is even. Well, that sounds familiar, right? That's what we just did. Done. We did this already. We did this already. So that's done. Okay, so let's do the second half. We need to also prove, for the biconditional, we need to prove that Q implies P. So, i.e., what does this say? It says x plus, so if x plus y is even, then x and y are both even. I'm going to say, well, hey, wait a second. I mean, here's how you would start, right? You would say, okay, we're assuming this is even, so we're assuming x plus y is twice an integer for an integer k. And then we want to show that x itself is 2 times an integer and y itself is 2 times an integer. I don't see a clear way to do that, right? It's certainly not as readily apparent as this. And yeah, of course, if you think about this is just not true, right? This whole statement is not true. This is not true. And the reason it's not true, like, do we have to go prove that it's not true? Well, here's my proof. 3 plus 7 is 10. 10, their sum is even, but 3 and 7 are odd. So, but 3 and 7 are odd. That's my proof. You might say, well, wait a second. How come you're just doing one example here when that doesn't work here? Well, it's because I'm trying to show that if the sum is even, then these two are even. Always, right? For all x and y. I just found two numbers where it does not work, right? I found an example where the sum is even, but these are not even. The numbers are not even. So that disproves it, because it's not true that, this follows for every number x and y. So this is called a counterexample. This is a counterexample. This is a counterexample. And so what do we actually conclude? Like, this statement is false. What about the overall statement? Well, the overall statement is false, right? This whole thing is false because it's an if and only if, right? So we need both of the implications to be true. Oh, I should just write. This is so important. I should point out. So this is really important. Yeah, to keep in mind. Yeah. So generally, yeah, I'll say generally because it's not true always, but this is a good rule of thumb. So to prove a statement is true, you need to write a proof, like a full proof. A full proof. So we can't just do this. We had to do it in general. But to prove a statement is false. False. We just need one counterexample. One counterexample, like here. And so I just want to stress that this is not always the case. That's why I have generally here. Yeah. So for example, the statement could be, there exists a number such that so-and-so. And then to show that's true, you just have to find a number. To show it's false, you have to prove that it won't work for any number. But in general, yeah, this is how you would proceed. Okay. Let's do one more proof. And we'll talk about the idea of proof by contrapositive as well. So let's stick with even and odd for a minute. What should we do? Let's prove yeah, so let x be an integer. Prove that. Prove that. Let's do an if and only if x is odd if and only if x squared is odd. Okay. Well, you already know what to do. Right? We see the if and only if, so we've got P and Q. First step, prove P implies Q. Okay. This one is true, by the way, unlike the other one. I'm not trying to trick anyone. So let's prove P implies Q. So how do we do that? Well, we start out by assuming this. So yeah, well, let's just be really clear. So here's the exact statement I'm trying to prove. If x is odd, then x squared is odd. Then x squared is odd. So you want to assume, so let's let x be an odd number. So x is going to be an odd number. Remember our form of an odd number, 2k plus 1. That's where we start. I'm just unraveling the definition. And now I need to show this. All right, I'll emphasize that I forgot to do this last time, but for some integer k. K is an integer, it's not irrational number or anything like that. Okay, then, well, let's square it. I want to show that square is odd. So the square of 2k plus, or the square of x is 2k plus 1 squared. As x is odd, we can write it in this form. And I mean, I probably want to do some algebra here. Often you have to do some algebra steps. 4k squared plus 4k plus 1, if you expand that out. And, well, are we looking at an odd number here? I feel like we are, right? We have a multiple of 4 plus another multiple of 4, and then we're adding 1. That's bound to make it odd, but let's just make it obvious. How do we make it obvious? Let's try to write it in exactly that form, where it's 2 times an integer plus 1. 2 times, do you see what I should write there? I'll leave that plus 1. I want that plus 1. So it's 2 times, I can factor out 2 from these first two terms. I can't factor it out from there, but I don't want to factor it out from there. I want to leave the 1 there because that's an odd integer. Great. So which is odd? So we're done. Well, we're halfway done, right? We did P implies Q. We implied that, we did X is odd implies that X squared is odd. Now I have to do Q implies P. And just to be clear, what is that? Is if X squared is odd, and X was odd to start with, then X is odd. Somehow this one seems a little more difficult. It's true, but yeah, it seems a bit more difficult. But let's try. So where do I want to start? I want to start with this. This is what I want to start with. So let's let, I'm doing Q implies P. So this is my Q. This is my P. So we start with Q in this case, right, the if part. Let X squared be odd. So X squared is of the form 2k plus 1 for some integer k. Then I want to somehow show that X is odd. But how do we get X from this? I guess I could take a square root. That's a bit strange. Not sure I can write that as 2 times an integer plus 1. So I'm a bit stuck here, actually. You might see an idea here, but it's certainly not as straightforward as up here, where you just write X like that, and then we plug it into X squared, and then we're done. So yeah, this seems tricky. This seems tricky. It's just me thinking out loud. And so there's another idea that we can use here. So let's recall something. Q implies P. We don't have to prove Q implies P. Q implies P is equivalent to, not P implies Q, that would be the converse, those are not equivalent. But Q implies P is equivalent to the contrapositive, where I put not on the end and switch them. So not P implies not Q. And what would that be? So that's that's the contrapositive. Contrapositive. Let's write out the contrapositive just to be clear. So it's saying not this. So if X is not odd, I guess another word for not odd would be even. Then X squared is not odd, is even. That's the contrapositive. So not odd. That is equivalent to this statement. Okay. And I feel like this is much easier to prove, right? How do you prove this? So, before we get ahead of ourselves, let's try to actually write out our proof. So here's our proof. So proof of 2. This part. Often it's good to make it clear to the reader that you're proving a contrapositive instead. So we'll use a proof by contrapositive. This is a proof technique. So instead of proving P implies Q directly, I'll prove the contrapositive, not Q implies not P. Use a proof by contrapositive. So we'll suppose X is even. X is even. And I want to prove that X squared is even. What does it mean to be even? So X is 2k for some integer k. For some integer k. Then I want to show this. X squared is even, the then part. Then I'll do some algebra here. X squared is 2k squared, and the only thing I see to do with that is square both of these, so 4k squared. And now I'm trying to remember what I'm doing, so I want to show that this thing is even. Well, that is 2 times an integer. Better yet, it's 4 times an integer, but it's also 2 times an integer. I'm just making it super clear. So this is 2 times an integer, which is even. Okay. Great. So we prove P implies Q, then Q implies P. We're done. You might say, well, wait, this seems like cheating almost, because it seemed like this statement was very much easier than this original one. It's definitely not cheating. These are the same statement. They are totally equivalent. And this brings up some good advice, maybe. So advice, if a direct proof seems hard, like maybe the then part, where are we? The then part here, that's a bit more tangible than this one. In that case, you often want to try a proof by contrapositive. So you should at least consider a proof by contrapositive before giving up. Contrapositive instead. It often just makes it easier to think about in certain cases. Some cases it makes it harder to think about. So I would try to direct proof first. If it seems hard like it did here, you can try a proof by contrapositive. And it's exactly equivalent to proving the original statement. Okay, I should end the video there.